Yeah, thanks, Eugene. Yeah, sorry, I think I can't really see the audience, but that's all right. So yeah, if you recall, I think I think it was in May, we last year. We talked about kind of how, well, at least how technology developed up to GPT-4. I mean, since then, I think we've had well, if you follow this space, we've had quite a barrage of let's call them that, of AI development. Some of them more important than others. If you happen to be associated with the AI news topic on YouTube, I think you'll get several videos a day talking about shocking developments. Huge week in AI, the world is about to change, and so on. I think now we are in the final countdown. That's the current stage of AI development. The final countdown is, of course, due to the cryptic tweet from Sam Altman in response to Jimmy Apple's an anonymous account saying, "Patience, Jimmy, it will be worth the wait." That's the latest on the state of AI. But that's not really what we are here to talk about. We're really to show, I guess, to show with some examples. Oh, just to check, maybe Eugene, do you know, is the other slides coming up okay? Just want to the slide change. Yeah, good. Okay.
Yeah, we can see them.
Yeah. So I mean, what would make for a truly huge week in AI? And well, if you think about it, of course, it's the ability to self-improve to some degree. And it's unclear whether the standard LLMs current generation of LLMs perhaps can't self-improve without help. However, I mean, all pieces are really already there, as I will show today. So with nothing, knowing absolutely nothing, but very rudimentary prompting, you can really create I guess a genuinely self-improving AI system, at least restricted to a particular task, which I will introduce in a second. So it's really the simplest possible task, which is, I guess, text classification. However, my contribution to this was really minimal. All I did is just concatenated some text files and pasted them in, and then pasted things back. That was about the intellectual level which I was involved. And I mean, the performance really does improve. So, I mean, it's not difficult to extrapolate that with a little bit of help. I mean, the next um, perhaps even the very next generation of AI systems, given a particular task, will be able to go about systematically about assessing own performance and trying to improve it. Um, so, um, okay. So the problem I will use as the example is an item kind of a string text classification problem. So we have item descriptions in the form that they appear on invoices, and we would like to work out whether those items are eligible for an insurance offer, extended warranty. And generally, to be eligible, an item has to be a physical, non-perishable, or consumable item. So something like a loaf of bread wouldn't be considered eligible for extended warranty. Neither would perfume or the like. Some car parts with expected lifetimes are a bit of a more, like tires, are potentially more difficult, although yeah, we don't really have to deal with this. And of course, we have to. The reason we want to solve this as a linear classification problem is just because we have to have a pretty rapid pretty quick response, because it has to appear whenever you refresh the page. And since we like, if you use one of the embedding models, you get basically the text converted into vectors um, of, well, at least 1,000 dimensions. You want maybe let's say a few 10,000 or more examples to make sure your linear classifier is saturated. You're not losing accuracy just from the uncertainty there. Now, to create this data set, uh, just naive prompting, apologies, with GPT 3.5 gives you accuracy of about 70%. You do get about 90 with GPT-4, but that's that doesn't provide such a dramatic gain, so I wouldn't demonstrate. So maybe how could we go about it? Well, the way to do it is to change the prompt. Instead of just giving the definition, you could add examples and perhaps ask to reason step by step, those sorts of things. So basically, prompt modifications. But how do we go about systematically searching, or searching for at least a better prompt? Well, there was this recent framework called DSPy, which is, I guess, a way to, and I'll talk about it in a second, actually. Um, yeah, I'll introduce the framework in a second, and just quickly to show what the data set looks like. Yeah, data set contains of really two relevant fields: item descriptions and whether the item is insurable. Um, and it looks something like this. So you have your item description, and insurable true. I guess can opener, sure, why not? Um, the freeze, some sort of low voltage fridge, sure, insurable, and so on. VIP membership is not insurable. Um, whatever these are contact lenses. These are also not insurable. So that's the just this data set with a few just about 100 examples was put together manually. Um, okay, so what is, yes? So this talk isn't really about DSPy per se. In fact, could be some other framework, but just DSPy happens to be the framework that's specifically about prompt optimization. Uh, as a warning, it's probably not really ready for production use, but so I wouldn't recommend using it for production, but it could be good for prototyping and so on. It has some interesting concepts. Anyways, so it's an attempt to make the kind of working with LLM-based systems look a bit more like PyTorch, even though, of course, it's nothing like PyTorch really, but it has the similar structure, conceptually has similar structure. So it has modules and it has optimization step, similar to the way you define your network structure, then you run an optimizer. So the modular structure in PyTorch, you have mappings from tensors, and then you have modules, and then tensors. You can chain modules together, provided, of course, you have to make sure at runtime that the dimensions match up, or it doesn't work. And in DSPy, you have these input fields and output fields, and you can have intermediate steps and kind of a graph structure. In our case, input field is just the item description, and the output is whether it's insurable or not. But we could have intermediate fields if we had a more complex structure, like we could generate reasoning, then we could critique the reasoning and so on, and then kind of reflect and make final. So we could introduce a more complex kind of dialogue structure. And there are different module types that are already built in. And then we talk about optimization, right? Within the in PyTorch, you would have your different losses, like the um, sum of squares or cross entropy, and you have the optimizers, whether it's just the gradient descent, Adam, or variations on Adam. Yeah, and we minimize the loss over the training set. And in this DSPy framework, we define a metric which tells us on the set of examples that we have, how to compare an example with the output generated by the LLM. It can be the exact match, it can be approximate match, like you can count how many keyword overlap. You can basically define whatever metric you want. Then there are different optimizers that are built in, and an optimizer is just a way to perturb the prompts essentially, or the prompts that the modules generate, and then see how it affects the metric. Of course, it's not real optimization. It's very much sort of heuristic optimization. You don't have a gradient, so you just really reduce to kind of changing things. But potentially you can do it greedily. So maybe you can have progressive improvement in a multi-chain situation. Now, if you actually go to the DSPy website, you will find there is a lot of, it's a little bit complicated. There is, especially if you read the paper, there is all this talk about parameterized prompts, compilation, teleprompters, assertions, and the examples. Even though you think classification is the simplest example, they don't actually have that example in their repository. So that's and in fact, I've tried to figure it out for quite some time, but the progress was was elusive. Um, so, but what you turns out what you can do um, is we can in fact overcome at least I was able to overcome my personal limitations in trying to address the to figure out how this framework actually works by concatenating the GitHub repo into a single string and pasting it into another LLM. Um, I think that's where the level of anyway, it was I was quite surprised that this worked, and indeed, the you will perhaps so should you be. I mean, it truly does mean that we can't be far away from reliable self-improvement if these things essentially work out of the box. So my contribution was really this. Basically a Python method to go through the DSPy GitHub repo and concatenate the files. So I put the README file at the start, and then directory structure, and then just dumped all the files in. Now it resulted in a fairly sizable file of of about 4 or 5 megabytes, but there was a bit of binary stuff, so I had to anyway restrict the file types to be only Python and so on. So a little bit of compression was needed, but not a lot. I had to delete about a third. And after that, what was possible to do? I've simply pasted this concatenated GitHub repo and the CSV file with the examples into the new Anthropic model. And this is, I think, the shocking part. it generated a working example 0 shot. Are you shocked? Well, I was pretty shocked. So that's really all I did for this presentation. Okay, which is yes. Okay, so what does that? And I mean, this one. Um, so yeah, so that takes about 2 minutes, right? And I'm pretty sure that there is no classification example in the examples. Well, I couldn't find it. And I had to add it. Like initially, it just created the examples in the code. So I just asked, please make sure read them from the CSV file. And I also wanted to compare it to a naive strategy. And this is what I got, right? So basically, we can quickly have a look at the code that plot 3 has generated. Just to give you an example, just to give you some sense for how this framework works. So we define basically our match function. So this is our metric, and basically the metric, you get a 1 if your ground truth matches the prediction, and otherwise you get a 0. So that's very simple. Um, then we define this item classifier DSPy module, okay, that basically just based on a simple chain of thought prompt. Then read in the CSV file of the type we've seen before, define our, say that we're using GPT 3.5, create, I don't, again, I really don't know what the teleprompter is. I think it's probably, that's what DSPy calls it, but I think it's really more like an optimizer. So it's basically, this is the method for generating few shot prompts that works together with chain of thought. So it basically gives examples of reasoning in the prompt itself, which is pretty interesting. And this is the very simple example where you just give 5 labeled examples from the data set and insert it to the prompt. That's kind of our baseline comparison. And then essentially you just evaluate the accuracy. So that's all. But basically, I said, well, essentially, this entire script was generated 0 shot based on the request. Please give me an example. So that's okay. And then when I run this, this is what I get. So the simple prompt where you just provide the examples. Of insurable and non-insurable items. 5 examples gives you this score, and the one that DSPy has generated using this particular optimizer with these parameters has accuracy of 91%, which, by the way, like a handcrafted prompt that I had for GPT-4 to do this, also gave about 91, 92%. So it's basically we're getting now on this task similar to 0 shot GPT-4 performance. But what actually happened? Well, the generated prompt basically includes, in this case, I think 10 examples of basically reasoning. Um, so um, so this is, for example, here we have item description, then we have the which is this. Then we have reasoning. Let's think step by step on how we can determine the sign of that appliance. Since it's a common household unrisk association, we can say that it's insurable. I mean, again, this is not really a particularly amazing reasoning, but when these reasoning examples are generated, at least it makes sure that the output is correct. It doesn't actually check that the reasoning is correct. And also in this example, I haven't modified the example to actually add hints about what insurable means. So there are all sorts of limitations, but basically this is the prompt, and the prompt for GPT 3.5 contains 10 examples of reasoning taken from the data set, comparing it against the baseline, which only has item descriptions and the whether it's insurable or not. So that's really the kind of what we've seen, right? We've taken a problem and by using LLMs with some additional knowledge being, I guess, the research or thinking that the DSPy team has put into it, we've essentially been able to construct a system that's to some degree self-improves. Now for DSPy, now, all that said, I think it's still worthwhile checking out DSPy a little bit more because it's really great for prototyping complex LLM workflows. So, for example, you can look up, like this is, I think, a couple of months old. There was a paper called Alpha Codium, which is kind of like this LLM prompting strategy to improve performance on coding tasks. And it looks pretty complicated. You basically you enter problem description and tests, and then it generates the plan, critiques the plan, generates solutions, ranks solutions, generates additional tests, and so on. So it's all a little bit, and then it has this this step actually, which is actually trying to test the code that's been generated. So you actually run the code and so on. So partial and not complete, but partial implementation of this, quite a big exercise to write with prompts and kind of string manipulation. You can write that in about, I think just 1 second. I think I lost that German. I'll bring that up. Okay, 1 second. Yeah, I just want to show what it looks like if we okay. There we go. So this is the entire kind of a good part of the DSPy implementation for this algorithm, which is very straightforward. And I guess if you understand the typing, it can be a interesting thing to try and prototype more complex LLM-based systems. So that's really the main thing. But I guess the big conclusion from this is that, I mean, you can clearly see that with the language models with large context windows, right, you are essentially able to provide enough context to, even though the models themselves aren't trained on DSPy and so on, because the model implementation is actually after the training date, even for Claude, you're able to kind of get the models to more or less learn how to use themselves. I mean, it's not perfect, but we're very, very close, right? And that's perhaps to date, this has been the biggest limitation when you're working with something like GPT. Sure, it can write Python code, but it's been very, very bad at running like OpenAI API Python code. But I think with this large context models that are better at instruction following, probably the next Google release, the 1.5 Gemini release is allegedly very good at that as well, we will be able to essentially use LLMs to help us build LLM-based systems. And I think that will significantly accelerate applications. So that's, I guess, the main thing I wanted to show today. Hopefully everyone's shocked by the huge data.
I think you'll agree that was indeed pretty shocking as advertised and very to the point. So any questions, folks? Everyone's shocked. Well, in the absence of questions, and where are you anyway, Dimitri?
Oh, I'm in I'm in San Francisco.
Oh, geez.
Which is, that's right. It's, I guess, appropriate.
Well, we'd better leave Dimitri to it then. So please join me in thanking Dimitri.
Yeah.